show on the road here. So let's see. Homework is due next Thursday. Community office hours.
No lecture.
Yes, so to remind you that I'm going to be out on Thursday, so we won't have class on Thursday. But I want to have a makeup, so I'll send around, but Paul will do the best we can to try to find the time to do that. All righty, so let's see where we're at. So we're continuing our discussion of face-based representations, and in particular, we have this formalism that we've developed over a while now that says that we can, one way to think about a face-based representation is through an operator-ordered series. So if we have some operator, we can write it in a power series in terms of ordered products of A and A dagger. And the S-ordered representation then we obtain by just substituting for A dagger alpha star and substituting for A alpha, okay? And that gives us this representation. And what we showed is that we obtain that by the operator inner product between the operator of interest and the minus S ordered delta function, okay? So given our S ordering of the delta functions, we have this operator basis that forms what we call a operator frame, okay? It's a way of expanding any operator in the basis of these operators. And in particular, what we had is that the anti-normally ordered delta function is actually the projector onto a coherent state. Okay, that's kind of interesting. And because this is an operator frame with this duality here, we can, as we said, expand any operator in this frame, and we have this expression. That is to say, any operator A can be expressed as in terms of this representation, as a superposition of delta functions. Okay. And that also gives us a way, for example, of looking at the trace inner product between two operators in terms of that representation. So in particular, the density matrix, if we look at its representation, those are our quasi-probability distributions, okay? So we're defining the representations given S, W sub S, and they have all these different names. So the symmetrically ordered representation is what we get when we trace with the the normally ordered representation is what we get when we trace with the anti-normally ordered delta function. And given that that is the projector, we get this expression, okay? So this is what we call the Q function, or the Husini distribution. The symmetrically ordered guy is what we've been talking for a while. This is the Wigner function, and the anti-normally ordered representation of the density matrix is our friend, the Glauber P representation. So these are all different sides of the same coin, all right? Right, and so importantly, because of this kind of duality, what we see here is that if I look at, say, the expectation value of an S-ordered moment. This could be a normally ordered, anti-normally ordered, or symmetrically ordered, given this expression that we have over here. What I have is that this is equal to so a way in which we can calculate these moments is by thinking about them from a sort of semi-classical perspective. If we were to think about these as probability distributions, the moments of the distribution are these polynomials averaged over the distribution, okay? But here we see this kind of duality over here. So if I'm looking at, for example, if S is plus 1, if I was looking at the normally ordered expectation value, then I have to do this average with the anti-normally ordered representation of the density matrix, which is the P function, which is what we knew from the beginning, right? That the P function, the Glauber P function, was developed as a way of thinking about what was classical from photon counting, and as we've discussed, when we're talking about photon counting, the Glauber theory tells us that what we measure are the normally ordered expectation values. If we were symmetric, then this would be the Wigner function. If we wanted to calculate the anti-normally ordered products here, we would average with the Q function. Okay, so there's this duality here. I might want to mention here that the notion of the characteristic function. So the characteristic function we define as the Fourier transform of, in the complex plane, of quasi-probability distribution. Okay. Now, the characteristic function is something that comes from statistics, from classical statistics. And the reason it's called the characteristic function is that it is the generator of moments of the distribution. And we can see that in the following way. Suppose I take the partial derivative of this with respect to alpha. Okay, if I take the partial derivative, let me take it the derivative, doesn't matter. I'll take the partial with respect to alpha star, just for the heck of it. What do I get? I'm sorry, what I mean is with respect to beta star. Okay, so this is a function of beta and beta star. I'm going to take the partial derivative with respect to beta star. What happens? I bring down a factor when I take that derivative of minus alpha. So if I take this derivative and then I set I get everyone see that? I took the partial derivative with respect to beta star, and then I looked at what that is at the origin of this function. So the derivative at this origin is in fact this moment. And in fact, if I look at the partial derivative of this with respect to beta to the power m, and this to the power n, with a minus 1 to the n, then this is equal to the derivatives of all that stuff will give me a alpha to the n, alpha star to the n. Yes?
So you're treating beta star and beta as two independent variables?
That is correct. So that is when we have a function of a complex variable, we have to think about the variable and its complex conjugate as independent variables that we take the derivatives with respect to. Yeah, that's a complicated story of complex analysis.
Does that mean that like the d squared alpha is like d alpha star?
No,
No.
that is not true. But d alpha squared is not the same thing as d. This I have to take respect to a different variable. These are different things.
I see.
As is this. And they're all different derivatives.
I see. But that like d squared alpha is then just of alpha, not alpha star.
Second derivative with respect to alpha, but not alpha star. Okay? Very good. But the point here is this is just what we said over here.
D squared alpha, I think that's the measure. Is what
Oh, this thing.
That's what.
No. D squared alpha is d real alpha times d imaginary alpha. That's what that's defined to be. Okay?
Thank you for.
Yeah. Excuse me.
Thank you.
Yeah. That's what this is defined to be. Okay, so the point here is that another thing to keep in mind, and this is very useful, is that if you want to calculate moments, which we often do, because these are the things that we're often measuring, we can calculate them as the derivatives of the characteristic function at the origin. That's why it's called the characteristic function. It's the thing that gives me the characters, which are the moments of the distribution. Okay, so what we were also discussing last time is the idea of the existence. I always like to think about existence. So from this expression that we said, the relationship between the characteristic function and the quasi-probability distribution, right? So the distribution here is the inverse Fourier transform of the characteristic function. Then this thing exists if the characteristic function is finite, that is to say, if it's square normalizable. Okay? So if the Fourier transform is square normalizable, then I can take the inverse Fourier transform and get this. Okay? Now, the S-ordered characteristic function we can obtain, as we know, by tracing with the minus S-ordered displacement operator. And that is related to the trace with the symmetrically ordered through this factor. Okay? So, what we see here is that a few things. Firstly, for the Wigner function, because this object over here, the trace of rho squared by everything we've just discussed is in fact the square norm of the characteristic function, which is always less than or equal to 1, is finite, and this is this for the Wigner function. So that is, the trace of rho squared is this, where this is the Wigner function, the symmetric characteristic function. This is always finite, so the Wigner function always exists. Moreover, the normally ordered guy, according to this, is e to the minus beta squared over 2 times that for the symmetrically ordered guy, so in this case, because this is very heavily damped, that means that this is square normalizable. So that's, of course, what we expect. What it's saying is that the Q function exists. But the P function is that the anti-normally ordered characteristic function, which is the Fourier transform of the P function, blows up generally. And it blows up unless this thing falls off faster than this, okay? In fact, there is no pure state where that is true. The only state where this is just barely cancels that is a coherent state. For a coherent state, this thing is equal to minus that, and we get a constant, which means the Fourier transform of something which is a constant is a delta function. So the P function is a very ill-defined function. Yeah?
When we first introduced the P function last
Yeah.
semester, you talked about how, so we only really talked about it in terms of statistical mixtures of coherent states.
That's correct.
And that in part is because that's the only way.
That's the only way that it actually is a meaningful function.
And we talked about it in terms of a positive probability distribution, like an actual probability distribution.
Yep.
Classical state, and if it's negative, it's
Or something negative and ill-defined, yep.
if it's, so when we were talking about this function, the P function, as a determinant of what is classical like,
Yeah.
if you can write it, it's not that this has removed that, it's just saying there's a lot of states where you can't define P, and so.
Yeah, I mean, I think that's it's a good and perhaps subtle point. The only states for which this is well defined are for the mixed states. The only pure state where we would barely say that's okay is for a coherent state. So for a coherent state, what is the P function? It's a delta function. We're okay with that in physics. Okay? It's barely okay, but we'll say it's okay, right? What is the Wigner function? It's a Gaussian, right? It's a Gaussian that has a certain width that's related, that we know in this case that gives us delta x squared equals delta p squared equals a half. Okay? What is the Q function of a coherent state? How would you calculate it? So how do you calculate the Q function? The Q function is just the overlap with the coherent state, right? You don't have to get in this case, right, the Q function is this, okay? So if you have the state, it's often quite easy to calculate the Q function, which is this. So what is that? It's a Gaussian. How would you calculate it? What was the answer there? How do you calculate it? You use the displacement operator, right? And then you have to think about how you multiply two displacement operators together. And the answer is that this is equal to this. So how does the Q function, so this guy was a point. So let's just draw a sketch. if I had a coherent state with certain alpha, the P function is a delta function, it's a point there. The Wigner function is a Gaussian. And the Gaussian has these RMS values, 1 over root 2 inside. What about the P function? I'm sorry, the Q function. How does it differ from this? It has a different width. Is the width bigger or smaller? Bigger, right? Because this guy, remember, we have e to the minus x naught over 2 sigma x squared, etc. xp minus p naught squared over 2 sigma p squared. In this case, what is sigma squared? Oops. So, we have to write this out. This is e to the minus x naught squared over 2. This is e to the minus p naught squared over 2 because of that factor of root 2, right? So in this case, this is 1, and this is 1. It's got twice the width of that guy. So the Q function is a chubbier version of the bigger version. It's a more smeared out version of that, okay? Now, in fact, somewhere written over here, yeah, this relationship over here tells us a few things. It tells us that if I look at this relationship here, it tells me that I can find the Wigner function, which is if this guy was equal to -1 and this was 1, and that's the other side, the Wigner function is a convolution of the P function with a Gaussian. Okay. And the Q function is the convolution of the Wigner function. With the Gaussian. So we can think about these different quasi-probability distributions. In some sense, this is the P function in some sense is the most fine-grained function, but that fine-grainedness makes it ill-defined. But when I smear it out with this delta function, it's completely well-defined. The Q function is even a more smeared out version of the Wigner function. But interestingly, this thing makes it that this is always positive. Whereas the Wigner function can be negative. All right, very good. So what are some of the takeaways from all of this? Okay, some of the takeaways we have is the notion of classicality depends on what we measure. I want you to think about that. I want that to sink in for a moment. Because what it's telling us is that when we say something is classical, what we're saying is predictable with classical statistics. That's why we're defining what it means to be classical. And we can have different measurements that we can do which may or may not be predictable by a classical statistical theory. So for example, if I have a squeeze state, then the Wigner function is positive everywhere. Whereas this thing is negative and singular. And since the Wigner function is the thing that I can use to predict the statistics of homodyne measurement, then what it says is that if I have a squeeze states, homodyne measurements are classically predictable. Whereas we know that the P function is the thing that we have that predicts the statistics of photon counting from the Glauber theory. So what this says is that photon counting is not classically predictable. You can ask whether there are states where nothing is classically predictable, and the answer is yes. If I have pure states that are not Gaussian, then none of the distributions would allow that. Okay. So, interestingly though, you remember we were talking briefly about the story about boson sampling, right? So, you remember in boson sampling, what we have is we have linear optical network. We have things like phase shifts and beam split. We have a beam splitter, goes into something else. There's a phase shifter over here, and it bounces off the mirror, and then this guy bounces off over here. Well, that's a Theorist beam splitter, but okay. And then there's one. And we have all these different input modes and output modes, where we just have beam splitters and phase shifters. And you remember what we said is that the output annihilation operator in any mode was related to the input by some unitary transformation that is just the classical, and how the classical amplitudes transform. So this is what it means to be linear optics, okay? And and that seems 100% classical if I sent in, for example, a coherent state. Then what I get is that my output coherent state is related to the input coherent states exactly as I expect classically. Every classical amplitude is transformed as we expect. Okay? However, what we also discussed, and so there's nothing, if I do this, there's nothing quantum about this. If I send in lasers through this linear optical network, I'm going to get out the laser beams with the electric field amplitudes transforming as we predict by classical Maxwell's equations. And we can describe those by coherent states. However, interestingly, if I were to send in single photon states, identical single photon wave packets into this, the state that comes out of this is something that has a probability distribution of some number of photons in each of these modes that would be impossible for a classical computer to simulate. The probability distribution is so complicated due to all the multi-photon interference that there's no way it would take me an exponential amount of power in the number of modes to be able to predict how many photons are in each of these modes. And if I try to sample from that, I'm going to get a random number of photons that I could never simulate. Okay? And that's one of the ideas of how people have tried to demonstrate what we call quantum supremacy. We don't like to use that word, quantum advantage. But yes, first, Omar.
If I can prepare any state,
Yeah.
then is this universal?
No, it's not universal for quantum computing. We can talk about that another time. But it's not a universal quantum computer. It just produces a state that doesn't have an efficient classical description. Okay, but I'm sorry, Benny, you had a question.
If you're not going into hints, but
No, I am.
oh, okay, sure. So if I were to translate these single photons into like an average photon count, which would correlate to some intensity detected on a detector, would that intensity just be wrong? Like, would that classical intensity just be wrong?
Yeah, I mean, as we know, we have some things. For example, if we had 2 photons on the spleen splitter, what do we see in terms of the amount of intensity I get here? What we know is that either both photons go this way or both photons go that way. Classically, I'm always going to see some intensity on both of these detectors. The Conlow-Mendel interference is the simplest example of the multi-photon version of it.
Which can't be described classically.
Which can't be described classically. But here's an interesting fact. Suppose instead of single photons into each of these modes, I put in a squeeze vacuum. Now, we just said it's kind of classical, right? And I can describe that, the transformation on that in terms of what happens, say, to the Wigner function, we're going to talk about that in a moment, efficiently. So I could write down the Wigner function for the output state. In fact, if the Wigner function of the output state, so let's say I have a Wigner function of the input state, which I'm going to say is a function of alpha and alpha star. I'm going to be very careful that we can say it's really a function of 2 things. But the Wigner function of the, let's say this is, there's some set of modes here. The Wigner function of the output is equal to the Wigner function of the input with a Bogoliubov transformation. So each mode is describable, is transformed according to a squeezing transformation, which we know is a Bogoliubov transformation. The transformation due to linear optics is efficiently describable on the Wigner function. So that seems pretty classical. I have a classical description of this thing. However, if I asked what is the probability of photon counting, of seeing n photons in any of those modes, in fact, that's completely impossible to do efficiently classically. So even though the description of the state can be thought about as classical from the point of view of homodyne measurement. If I were to try to do photon counting on description, there's no way I could predict the probability that I'm going to see that in any efficient way. It would take an exponential. And so one of the experiments that are done now in trying to demonstrate quantum supremacy in photon mechanics are done with so-called Gaussian photon counting. It's not really Gaussian. The state is Gaussian, but the measurements are not. Okay, so that's an important takeaway message that I wanted to describe, that what we describe as classical depends on what we measure. Yes?
Does there exist any sort of context where if something is defined in B but not well defined in one of the other ones?
No, the other ones are always more well defined because they're more smeared out.
So each one is strictly contained inside.
That's
the
correct.
I see.
That's correct. All right, very good. All right, so let's see. I think I've said everything I want to say about that. I want to talk about dynamics. Okay, so we've described how we represent the state. We described how we can represent operators. We described how we can represent the expectation value or the probabilities of outcomes. But now I want to think about dynamics, okay? And let's just think about, we have a Hamiltonian. And so we have Hamiltonian dynamics, okay? And what I'm particularly interested in here is classical versus non-classical dynamics. What does it mean for the dynamics to be classical, and what does it mean for the dynamics to be non-classical? And we have a way now of comparing them because we have a phase-space representation. We can compare classical dynamics in phase space to quantum dynamics in phase space and see how they differ and in what kind of dynamics generate states that are non-classical in the sense of they differ in their dynamics. Okay, so let's begin by just talking about classical dynamics, classical Hamiltonian dynamics. Now, I know we don't teach classical dynamics anymore. What the heck, man? But anyway, I hope you had it, and let's just say a couple of words about that. So if I just think about a single degree of freedom, let's go back to our friends X and P. We have Hamilton's equations of motion. Which tells me that X dot is the partial, so here the Hamiltonian is a function of X and P. And P dot, those are Hamilton's equations of motion, right? And it says if I have a phase space and I have some point in phase space, it undergoes a trajectory according to these equations of motion, right? Now, I can think about, to compare quantum and classical dynamics, I want to think about a probability distribution of phase space. Because again, when we're talking about classicality, we're always comparing our quantum system, which has randomness, to a classical statistical theory. So what we don't want to think about a point in phase space, we want to think about a probability distribution on phase space. And of course, each point in this phase space moves, and I end up with a different probability distribution. As you know, I hope you know, you have the Liouville theorem, which tells you that the area is conserved and all of the like. But the point here is I have some probability distribution on phase space. So this might be at time t equals 0. This is the probability distribution, okay? Now, this probability distribution we can kind of see just from the fact that it's coming from this classical flow, that the probability of the particle being at this position and this momentum at time t is related to what the probability of it being at this momentum and this position at the time backwards. That's to say, this is equal to does everyone see that? So I'm saying the probability to be at this position and momentum at time t is the probability of it being at this position and that momentum on the backward trajectory. Okay? So with that said, I can get the differential equation for the probability distribution just using the chain rule. This is going to be the derivative with respect to x at minus t, the partial derivative of the probability distribution with respect to x, plus the derivative of p at minus t, the partial derivative of the probability distribution with respect to momentum. And using the chain rule, that's then minus x dot dp dx plus, or minus p dot, the partial of the probability distribution with respect to momentum. But using Hamilton's equations over here, what this tells me is that this is equal to the partial of the Hamiltonian with respect to x times the partial of the probability distribution with respect to momentum, and then I have minus dh dp, the probability dx. Okay? This, have you ever seen this before? I don't know if you guys learn this stuff anymore, but anyway, this is our friend, which is known as the Poisson bracket. So the Poisson bracket is a particular differential operator and tells me thus that according to classical dynamics, the probability distribution on phase space evolves according to this partial differential equation. This equation is known as the Liouville equation. Okay? And it's related to the classical flow on phase space. Okay? Yes?
Why did you have to go back in time? I mean, when you have to consider p of x minus t, we could just take the derivative here.
This, by the method of characteristics, I'm saying I can do this partial derivative. This is the solution, and using it was a way of me deriving this equation from Hamilton's equations. This is the solution where x of t is a solution to this equation. In this case, I have the solution x of minus t where x at 0 was x. It gave me a way of deriving the equation of motion for the probability distribution using the method of characteristics. It's not so important. You can go back to your classical mechanics equation to see. I just wanted to derive it for you in the simplest way possible. This is the solution. So now the question for you is, how does this compare to quantum mechanics? Now that we have a probability distribution on phase space, we can think about the quantum dynamics of the state as a quasi-probability distribution on phase space. So, quantumly, we know we have the Schrödinger equation, which we'll write in the von Neumann way in terms of the density matrix, sometimes known as the von Neumann equation. It is the Schrödinger equation, but just the equation for the density operator. And we all remember this is the equation. This is the equation of how the density operator evolves in quantum mechanics. This, the Liouville equation, is the equation of how the probability distribution of phase space evolves. So what we want to do now is to ask, what is the equation of motion for the Wigner function, which is our distribution on phase space. We could do it for the P function, we could do it for the Q function, but let's do it for Wigner. I love Wigner, it's nice and symmetric. Okay? So, how would we do that? Yes, I'm listening. Did you have a question?
You use just the Poisson bracket because it's a probability, it's a quasi, but.
Yeah, so, yeah, well, okay, so what do we have to do? So, let's write this guy out. This is minus I over h bar. Okay. So, we need, if we want to look at, remember, the Wigner function is the Weyl symbol of rho, right? So we just have to take the Weyl symbol of both sides of the equation. So this guy is going to be equal to minus I h bar, the Weyl symbol of this operator, minus the Weyl symbol of that operator. Okay? So now we have another piece of formalism. We need to know, how do we take the Weyl symbol of a product of operators? I have two operators A and B, and I want to know what is the Weyl symbol of that product. That has a name. It's known as the star product. So this is what's known as the Moyle star product. And it's a mess to derive it. It's in the notes. How would you derive it? You have to just plug it in, right? You have to take the trace with the symmetric delta function, but then you have to think about, there's many different symmetric delta functions, you have to kind of compose them. It's a mess. But the bottom line is this. Oh, before I do that, I should make one more piece of notation. Come back to this guy over here. We're going to define a differential operator that has this horrible notation, but this is the way people do it. I'm going to do it like they do it. So what does this mean with these arrows in these different directions? So what this says is that the Poisson bracket of H with the probability distribution is H with this differential operator in the middle. Notice what it does. It applies the derivative to the thing on the left, that's partial respect to X, and the derivative with respect to P goes to the right. That's the notation of what this differential operator does, okay?
Is that the transpose of a derivative?
You could think about it that way. But notice that what is true here, okay, so I'll just leave that for now. So what one finds when one does this math is that this equals the following. I'm not going to derive it for you. It's a mess to derive it, but that's what that is. Okay? So, with that said, Oh, I should say that the opposite is also true. If I can also write it this way. Both of those things are true. The star product can be written in either of those directions. Okay. This is a horrible differential operator. What does this differential operator mean? It means that's what it means. Okay. So, with that said, the following is true. If I look at the commutator of A with B, and I look at the Weil symbol of that, that is A star B minus B star A, which is equal to A e to the I h bar gamma, right, over 2, minus e to the minus I using this rule. Okay. So, putting that together, I get the following. The rate of change of the Wigner function with respect to time, according to what we just wrote up there with the Moyle bracket, is equal to what's called the Moyle bracket and that's given by minus I over h bar, h star w minus w star h, which is equal to minus I over h bar, h e to the I h bar over 2 delta minus e to the minus I h bar over 2 delta w, which is equal to 2 over h bar, h, the sine of h bar over 2 delta times the Wigner function. Boy, that doesn't look so nice compared to what we had classically. I mean, written this way is deceiving. This equation looks pretty much like this equation. dp dt is the Poisson bracket of the Hamiltonian with the probability. All we got is, instead of the Poisson bracket, we have the Moyle bracket. But the Moyle bracket is this. Now, but here's where it gets interesting. What happens in the classical limit? How would we define the classical limit? Well, we can loosely say, as h bar goes to 0 is the classical limit of dynamics. The classical h bar goes to 0 limit is a little bit tricky, but I'm going to be fast and loose here. Okay. If I think about h bar goes to 0, then I can do an expansion of the sign in terms of the power series. Okay. And so let's do that. What I get if I do that is that this thing, the sine of this, remember, so in that limit then, the sine of this is this plus the next term, which is 1 over right? I have to take all those terms. I want to get the factors right. Let me just write it out over here. 3 factorial, excuse me.
Minus.
So, what we have thus, let me just get my notes here. Right, is that the equation of motion is equal to the following. I multiply this out, what I get is HW this plus the sum over n equals 1 to infinity minus 1 to the n over 2 to the n h bar to the 2n plus 1 factorial h 2n plus 1 w. And this is what? That's the Poisson bracket. That's cool. So what we see here is that, in the limit that h bar goes to 0, the dynamics of the Wigner function on phase space is the classical flow generated by the Poisson bracket plus quantum corrections that depend on powers of h bar and high order derivatives. Remember, these things will be third order derivatives and beyond of this thing, okay? So we can ask just a general question. I don't know if this is something you study in your quantum mechanics. Is you've heard of Ehrenfest's theorem? How would you define Ehrenfest's theorem? Because I think it's often confused. I'm curious what you think about. What is Ehrenfest's theorem? What does it say?
Gives you the dynamics of the expectation value of an operator.
It's something about the dynamics of the expectation value. And what is the theorem? What is Ehrenfest's theorem?
I think the way I heard it was the expectation the dynamics of a system should approach classical mechanics.
Yeah, so there's something about, does the expected value of something look classical? It's something about that. We can ask the following question. So instead of thinking about a point in x and p, I can think about the expected value of x and the expected value of p as a function of time. And I can ask, do these follow the classical trajectory or not? Okay, so I can look at the equations of motion for this. And ask, does this follow the classical trajectory or not? Under what conditions does it doesn't? Is that generally true? Do they follow the classical trajectories? Would it follow what we expect, what we would get from the classical theory? What is the condition for that to be true? Well, we can look at a simple example. Let's suppose my Hamiltonian was just kinetic energy and potential energy. Okay. Then we know that the equations of motion that follow from the Heisenberg equations of motion look like this.
this shouldn't be P over M, because doesn't,
Yes, oh no, sorry, P over M, not 2M, excuse me, absolutely. Yes. Okay, so now let's take the expected value of this. If this is going to be classical, the question is, does this if that were the case, then this would be the classical equation of motion. The mean x and the mean p would follow the classical trajectory. But this is not always true. So if I were to look, for example, say that I had a potential which was some quartic function of x, okay? Then the partial with respect to x, evaluated at x equals that, would be 4x cubed. But the expected value of this is this, right? But that is not equal to that. If it, to the degree to which it is approximately true, is the degree to which we would follow the classical trajectory. So there's something known as the Ehrenfest time. Which is to say the following: if I had this quartic potential and I started with some wave packet in here, to the degree to which the wave packet is very localized, it would see the local gradient, and the center of the packet would move according to the classical trajectory. The force is minus the gradient of the potential. The problem is that there are different forces at different points, and they interfere with one another. The degree to which this thing is well localized is the degree to which basically it's like a point and it doesn't see the spread. But when it becomes delocalized, then there are going to be different points, see different forces, and it's not going to move along the classical trajectory anymore. And interestingly, you might say, well, if something is macroscopic, that Ehrenfest time is probably, the Ehrenfest time is the time at which the mean x and p follows the classical trajectory. You might say, if I have something like a moon, that's going to be pretty macroscopic, and it's going to follow the classical trajectory because I can localize that wave packet extremely well. However, interestingly, if the dynamics are chaotic, we can get an exponentially spread and make that Ehrenfest time be something which we would observe very, very quickly, even for the moon of Saturn, which is chaotic, period. So that's an interesting paradox, which is the question of, we'll come back to that, under what conditions, why is the moon undergoing classical, this chaotic moon of Saturn undergoing something which is well predicted classically, which we know it is, even though the Ehrenfest time is very short. Yeah?
so you said that macroscopic groups should follow classical trajectory, but aren't cat states
The notion, I mean, we use the semantics, of course, are complicated. When we use the word macroscopic in different ways, we can talk about a macroscopic superposition, which we call the cat state. But we also know that we don't typically observe those in the macroscopic world. It's an interesting question. How can we obtain it? What are the conditions where we might be able to try to ensure that we can see that kind of superposition at the macroscopic scale? You might ask, how dynamically can the system evolve from us into a cat state? And that is something which we would have to say is not describable by the Poisson. These corrections have to become important in that situation, right? Right, so let's look at some examples. There's one last piece of formalism that I want to share. And that's known as the Bach representation. So here's one more way I can write the star product. Suppose I have an operator A, which is a function of x and p, and B, which is some function of x and p. And I want to look at the vowel symbol between them. That's the star product. I can obtain that in the Bach representation in the following ways. I'll explain this, what I mean, in a moment. So the way that I can obtain the vowel symbol and do the star product is by this operation where I've defined these differential operators q on the left, which is x plus I h bar over 2, the partial respect to p, and the right with the minus sign, and the differential operator p minus plus h bar over 2 d by dx. Okay, so this is a little weird, but let me explain what this means. It says that I can obtain this star product through this differential operators. Okay. Now, interestingly, that also tells me that the vowel symbol of an operator is that.
So is A and B being producted together?
This is a differential operator acting on this.
Or the left hand side? So those
Yes, those are just multiplied together. Sorry. Yeah. So if this is true, this is true because B is 1. Let's do an example. Let's suppose I have the operator A dagger A. How would you find the vowel symbol for that? The easiest way to do it is using the Bach representation. I don't have to go through the characteristic function and take its inverse Fourier transform. That would be a waste of your time. You just use the Bach representation. So the vowel symbol for this is equal to, according to that, I guess I wanted to do this also in X and P, I mean in A and A dagger. I could do it in X, but let's do it in terms of A and A dagger. The same is true here. If A is a function of A and A dagger, and B is a function of A and A dagger. Then the following is true. All right. Now let's try this. A is A dagger A. The Weil symbol for this I get by alpha star minus I h bar over 2 let me see, try to make sure I have my factors right. I should have said h bar in there. Yeah, those h bars are gone. Must be making things dimensionless. So what is the Weil symbol for this thing? Well, this derivative acts on that, gives 0, and then I'm going to get alpha times alpha star minus I over 2. Do we agree with that? Well, the answer is yes. And the reason is, if I write this in symmetric form, everyone see that this operator equals that operator? Because if I take the commutator, I get that. And the other rule of how we get the Weil symbol is write a symmetrically ordered power series and then substitute A is alpha and A dagger is alpha star, okay? Equivalently, if I look at the Hamiltonian x squared plus p squared, or the harmonic oscillator, the Weil symbol for this, because it's symmetrically ordered, is just alpha star alpha. Okay? So, here's where I want to conclude this discussion. If I just have a harmonic oscillator like this, what are the dynamics of the Wigner function? Well, my Hamiltonian is quadratic. My Hamiltonian is quadratic. What can we say about the effect of the Moyle bracket? We got the Poisson bracket, and then the corrections. But my Hamiltonian is quadratic in A and A dagger. So what happens to these terms? They're 0, because they're third order derivatives. In fact, the flow is completely classical. In fact, the equation of motion, if I were to write it down and put it back in terms of what I would find, is that this thing is exactly what we had classically. It would be equal to omega x d by dt minus p d by dx of the Wigner function, which is the classical flow. In fact, what this is equal to, if I write x plus it as r e to the I theta, and do the change of variables from the Cartesian coordinates to the polar coordinates, I get this equation. What is this equation telling me? What this equation is telling me is that according to the harmonic oscillator, every point is just rotating in the phase space by angle theta generated d by d phi. So if I started with a coherent state, it just rotates. What is also true, if I had squeezing, my Hamiltonian, let's write down the Hamiltonian that we've seen before. That's the Bogoliubov generator. It's got the squeezing parameter, say a squared minus a dagger squared, and then we have to make it real. What is the Weil symbol for this? Well, these guys are already symmetrically ordered. And so this is going to be equal to IR over 2 alpha squared minus alpha star squared. That's the Weil symbol. What is the flow? What is the equation of motion for the Wigner function when I have squeezing? What happens to these terms? There's nothing. It's purely classical again. As we expect, if we have squeezing and we start with a positive Wigner function, we should stay a positive Wigner function. The flow in that case would be, if I say I started here, I might get a squeezing Hamiltonian, which might say, give me a flow outward here and flow inward here and make the thing squeeze, but it's completely classical dynamics. What we have thus is that if we have a Hamiltonian which is quadratic in A and a dagger, then we have classical flow on phase space.
The evolution of the Wigner function is the evolution of...
It's classical flow. The evolution of the Wigner function is Hamilton's equation. So in order for us to generate a negativity in the Wigner function, we need to go beyond a Hamiltonian that is just quadratic in A and A dagger. We need something more nonlinear than that in order to get our non-classical states. All right, yeah, great. Yeah. And so that'll be one of our problems for homework, which is a paper we just submitted. So yeah, we're going to do that for Hamiltonian for homework. That'll be fun. All right. Yes.
I was gonna ask, does that also mean in A and A dagger is classical?
It's non-classical.
It's non-
Anything beyond, if we have something which is just only things that are quadratic in A and A dagger give me a vowel symbol which is quadratic in alpha and alpha star. And it's only when it's quadratic in alpha and alpha star that these terms are zero. The non-classical dynamics are coming from things that are beyond quadratic.
Which is the same as the condition for our air
Correct.
test theory.
Exactly. They all come together. Yes?
What if it's a free particle, so there's no potential?
Interesting question. If it's a free particle, then what is the vowel symbol in that case? So if I just had p squared, of course, in terms of x and p, that is the vowel symbol. Or equivalently, I can think about it as a plus a dagger squared, or a minus a dagger squared over 2. It's going to have an a squared, and a dagger squared, and then a dagger a, and a dagger, or with minus signs. And what's the vowel symbol for that? Well, it's going to be alpha squared plus alpha star squared, and it's all quadratic. So free particle is also a totally classical dynamics. Okay? A quadratic potential is, an inverted quadratic potential is what gives us squeezing, gives us hyperbolic. All those are the things that are classical dynamics. Anything beyond that is what we need to get non-classical states. But interestingly, and we'll come back to this, is the question of why don't we see this stuff in the classical world? I mean, this is, if quantum mechanics is the fundamental theory of the universe, and this is how things evolve, and I said we can certainly go in the macroscopic world and see times where, beyond the Ehrenfest time, where these things are non-negligible. Where are they?
H bar to the H bar over 2n. Sorry, H bar to the power 2n.
Well, they're there. They should contribute. Even though h bar is extremely tiny, these derivatives can be so big to make this term non-negligible, even in the limit as h bar goes to 0.
We have just quadratic Hamiltonians.
Sorry?
We only have quadratic Hamiltonians.
No, we certainly do not. We have many things that are not quadratic Hamiltonians. So we'll leave that for a little bit. A paradox to be described. All right. Remember, we're not having lecture on Thursday. We will have a problem section on Friday. Okay. I'll see you then. Yeah.